A silent flash in the void unleashes the sun's lifetime energy in a heartbeat. This is the domain of the Fermi Gamma-Ray Space Telescope and its vigilant heart, the Gamma-Ray Burst Monitor. Orbiting silently above us, this instrument is our dedicated sentinel, forever scanning for the cosmos' most catastrophic and cryptic explosions. By the end of our journey, you will understand how this unblinking watchkeeper reshapes our entire conception of reality, from the birth of black holes to storms that rage above our own heads. What triggers these universe-shattering blasts, and what surprising secrets has this monitor found by looking back at Earth? The answers redefine our place in the cosmic story. What does it mean to live in a universe that constantly broadcasts such violent, beautiful signals? In 2008, a new kind of eye opened in the sky. The Fermi Gamma-Ray Space Telescope rocketed into orbit, not to see the gentle light of stars, but to capture the universe's most violent and energetic whispers. Its mission was singular and profound: to map the high-energy frontier, a realm invisible to our own eyes and to traditional telescopes. This is the domain of gamma rays, the most potent form of light, born from matter pushed to its absolute limits. To understand the cosmos at its most extreme, from the crushing gravity of neutron stars to the relativistic jets of supermassive black holes, Fermi was built to listen. And like any good listener, it needed two distinct instruments to catch the full conversation. The first is the Large Area Telescope, a precision instrument designed to pinpoint and study persistent sources of gamma rays with incredible detail. It creates a detailed, sweeping map of the sky, but the universe is not just a steady hum, it is punctuated by sudden, deafening screams. For those, Fermi relies on its second instrument, the ever-vigilant gamma-ray burst monitor. While its partner maps the landscape, the GBM is the watchful guard, its 14 detectors constantly scanning the entire unshielded sky, waiting for the flash. It is the mission's rapid response system, the workhorse built for the sudden and the transient. Before Fermi, our view of the gamma-ray sky was fragmented, like trying to understand a symphony by hearing only a few scattered notes. Fermi, with its dual instruments observing together, gave us the full score. It transformed gamma-ray astronomy from a study of rare, mysterious events into a continuous, detailed observation of a dynamic and violent cosmos. This mission did not just add to our catalogue of celestial objects, it fundamentally rewrote the rules of high-energy astrophysics, revealing a universe far more active and explosive than we ever dared to imagine. These 14 silent eyes are the heart of the hunt. The gamma-ray burst monitor is not a single lens or camera in the traditional sense. It is a constellation of specialized detectors mounted around the body of the Fermi spacecraft. 12 of them are made of sodium iodide crystals, and 2 are crafted from bismuth germanate. This arrangement is not random. It is a masterpiece of engineering coverage, positioned so that at any given moment, some combination of these detectors can see every single part of the sky not blocked by the Earth itself. The entire celestial sphere is under its watch, but how does it actually see the invisible? The secret lies in the scintillator. When an incoming gamma-ray photon, a particle of unimaginable energy, slams into one of these crystals, it does not simply bounce off. It is absorbed. The impact deposits its tremendous energy into the crystal's structure, exciting its atoms. And just as a struck bell rings out with sound, these excited atoms release their energy in a tiny, precise flash of visible light. That is the scintillation, a literal spark in the dark. Sophisticated photomultiplier tubes, acting like ultra-sensitive light amplifiers, catch this faint glimmer and transform it into an electrical signal. The strength and timing of that signal tells the GBM everything: the energy of the original gamma ray and exactly when it arrived. This process happens in nanoseconds, over and over, as a burst floods the detectors with photons. The GBM's sole purpose is to act as a universal tripwire. It is designed for one thing above all else: speed. From the moment that first photon triggers a spark, the instrument's onboard logic springs into action, analyzing the pattern of which detectors were hit and how intensely. Within seconds, it can autonomously confirm a genuine astrophysical event, calculate a rough location in the sky, and send a rapid alert to observatories all over the world and in space, shouting, "Look here now." It is this relentless, automated vigilance that makes the GBM not just an instrument, but a guardian of opportunity, ensuring we never miss a chance to witness the universe's most fleeting and furious acts of creation. That instant of light within the crystal is just the beginning of a frantic, automated race against time. The spark from a single gamma ray is not enough. The universe is filled with a constant drizzle of high-energy particles. The GBM's true genius lies in its ability to recognize a pattern, to hear the sudden shout over the steady background murmur. As photons from a distant cataclysm flood in, the instrument's onboard computer is already at work. It analyzes the rate of incoming signals, watching for a sharp, statistically significant spike that rises and then falls away within milliseconds to minutes. This is the first critical filter. The software must decide if this is a real astrophysical event or just a random fluctuation, a glitch, or even a flash from our own sun. Solar flares can produce gamma rays, and even lightning storms on Earth can create brief, intense bursts of radiation called terrestrial gamma-ray flashes. The GBM's algorithms are trained to recognize the unique fingerprints of each, separating the cosmic from the local. Once a candidate event is flagged, the localization engine kicks in. This is a feat of real-time celestial triangulation. Remember, the 14 detectors are mounted on different sides of the spacecraft. A gamma-ray burst coming from one specific direction will illuminate certain detectors more brightly than others, casting a shadow of sorts across the instrument's geometry. By comparing the intensity and the precise timing of the signals across all 14 sensors, the onboard software can perform a rapid calculation. It pieces together which patch of sky, often an area about the size of your outstretched hand, is the source of the fury. This rough position is calculated within seconds, sometimes before the burst itself has even finished. This is the cosmic fire alarm, a blaring siren for astronomers. That rapid alert containing the time, duration, and most crucially, the sky coordinates, is immediately beamed down to the gamma-ray coordinates network, a system that distributes it to telescopes across the globe and in orbit. Within moments of the initial flash, robotic optical telescopes on mountaintops swivel to the spot, radio dishes tune in, and space observatories like the Swift satellite reorient themselves. The GBM's rapid trigger turns a fleeting, invisible explosion into a global observing campaign, transforming a solitary day to point into a multi-wavelength portrait of destruction. But the GBM's purpose stretches far beyond catching those singular, universe-shattering screams. Its constant vigil has revealed a solar system and a galaxy crackling with high-energy activity, turning it into a versatile monitor for a whole menagerie of cosmic and terrestrial phenomena. Our own sun, for instance, is a frequent subject. During powerful solar flares, the sun can accelerate particles to near light speeds, generating intense bursts of gamma rays. The GBM captures these eruptions in exquisite detail, providing crucial data on the most violent processes in our stellar backyard, processes that can disrupt satellites and power grids on Earth. Then there are the soft gamma repeaters. These are not one-time explosions, but rather the persistent, angry murmurs of magnetars, the intensely magnetic corpses of massive stars. A magnetar's magnetic field is so unimaginably strong it can literally crack the star's solid crust, releasing enormous flashes of gamma rays. The GBM detects these repeated outbursts, allowing scientists to study these bizarre stellar zombies in real time, watching as their colossal magnetic fields writhe and snap. Perhaps most surprising of all, the GBM's gaze downward has uncovered storms of a different kind. It routinely detects terrestrial gamma-ray flashes, intense millisecond bursts of radiation born within the thunderclouds of our own planet. These TGFs are created when powerful electric fields in thunderstorms accelerate electrons to near light speeds, which then smash into atmospheric atoms, producing a downward spray of gamma rays. The GBM sees these from above, offering a unique space-based perspective on one of Earth's most dramatic weather phenomena. And even when there is no specific flash to catch, the instrument's sensors are constantly measuring the steady rain of cosmic rays, high-energy particles from across the galaxy that bombard our spacecraft. By monitoring their flux, the GBM contributes to our understanding of the galactic environment through which our solar system travels. This incredible diversity of detection transforms the gamma-ray burst monitor from a specialist into a universal sentinel. It listens to the sun's tantrums, tracks the quakes of dead stars, witnesses Earth's atmospheric lightning turned inside out, and samples the galactic particle wind, all while remaining ever ready for the next great cosmic explosion. This frantic burst of data, a digital scream born from gamma-ray light, now begins a high-stakes race back to Earth. The journey starts within the Fermi spacecraft itself. The moment the gamma-ray burst monitor's algorithms confirm an event, they package a crucial summary, a data packet containing the time, the rough sky coordinates, and the burst's basic properties. This is the first alert, a cosmic telegram, but Fermi orbits far above the reach of most ground stations, so it cannot simply shout this message downward. Instead, it relies on a celestial relay network, the Tracking and Data Relay Satellite System. Think of these satellites as a series of signal towers in geosynchronous orbit, forming a continuous bridge between spacecraft like Fermi and the ground. Fermi beams its urgent alert up to one of these relay satellites, which then immediately downlinks it to a dedicated ground terminal at White Sands, New Mexico. This entire process, from detection in orbit to reception on the ground, often happens in less than 20 seconds. That initial alert is just the starting pistol. The raw torrent of data from the detectors, the complete record of every photon's energy and arrival time, follows a similar path but requires more processing. This full dataset streams down through the relay satellites to the Fermi Science Support Center, located at NASA, a Goddard Space Flight Center in Maryland. Here, the real detective work begins. Automated pipelines ingest the raw numbers, cleaning the signal from background noise, applying precise calibrations, and reconstructing the event with far greater accuracy than the spacecraft's quick-look estimate could achieve. Scientists and software validate the findings, ensuring it is not an instrument glitch or a known terrestrial event. Once verified, this refined data is formatted and sent to the public archive. But for the most urgent events, the gamma-ray bursts, there is no time to wait for this full processing. That is where the rapid alert system proves indispensable. The moment the initial coordinates from Fermi are received at Goddard, they are automatically injected into the gamma-ray coordinates network. This is a broadcast system serving thousands of astronomers and robotic telescopes worldwide. The alert flashes across the globe in seconds, landing in email inboxes, text messages, and automated observation queues. A robotic optical telescope in Chile might receive the notice, calculate the coordinates, and begin slewing to the patch of sky before the afterglow of the explosion has even begun to fade. This seamless pipeline, from a spark in a crystal orbiting at 17,000 miles per hour to a telescope on a mountaintop adjusting its gaze, is what transforms a fleeting burst of invisible light into a lasting scientific discovery. The data's journey ensures we are not just passive witnesses to these events, but active participants in their immediate study. The true power of this rapid response system was proven in a single, blinding flash on April 27, 2013. On that day, the gamma-ray burst monitor caught an event so extraordinary it would become a benchmark for decades to come, known as GRB 130427A. For nearly 20 hours, an afterglow across many wavelengths lingered, a fading echo of the initial cataclysm. This single event delivered a flood of data that tested our fundamental theories about how these explosions work. The most startling revelation came from the highest energy photons it detected. The GBM measured individual gamma-ray particles with energies exceeding 94 billion electron volts. To grasp that scale, consider that visible light from a light bulb consists of photons with about 2 or 3 electron volts of energy. This burst produced particles tens of billions of times more powerful, carrying the punch of a proton in a powerful particle accelerator, but born from a cosmic event billions of light years away. That detection alone pushed the limits of what physicists thought was possible from such a distant source, challenging models of how particles are accelerated in these relativistic jets. Crucially, the GBM's rapid and precise localization was the key that unlocked the universe. Its initial alert, distributed within seconds, enabled the entire astronomical community to swing into action. Ground-based optical telescopes pinpointed the burst's host galaxy, a relatively nearby one for such events at about 3.6 billion light-years away. This proximity, combined with the burst's incredible brightness, meant its afterglow could be studied across the entire electromagnetic spectrum, from radio waves all the way up to those staggering high-energy gamma rays. For the first time, scientists could connect the immediate, furious gamma-ray signal with the longer-lasting afterglow in exquisite detail, watching the physics unfold in real time across cosmic distances. GRB 130427 became a Rosetta Stone for gamma-ray burst science. The data cemented the connection between long-duration bursts and the collapse of massive stars into black holes. It provided direct evidence for the structure and composition of the ultra-fast jets that blast outward from the newborn black hole, and it offered stringent tests for the complex shockwave physics that generates the light we see. This one event, captured because a watchful monitor sent a timely alert, transformed a mysterious flash into a comprehensive textbook chapter, proving that the GBM is far more than a simple tripwire. It is the essential first witness in a coordinated cosmic investigation. For decades, the sheer variety of these flashes was a profound puzzle. They all lit up the detectors, but some were fleeting sparks while others were drawn-out cosmic fireworks. This simple observation, the duration of the burst, became the key that unlocked the door to their origins. The gamma-ray burst monitor's precise timing measurements allowed scientists to clearly separate the signals into two distinct families. Short gamma-ray bursts, as the name implies, last less than 2 seconds. Their light curve is a sudden, sharp spike of incredible intensity that vanishes almost as quickly as it appears. Long gamma-ray bursts, in contrast, can persist for many seconds, even minutes, with a more complex and rolling structure of peaks and valleys. This was not just a difference in length, it was a fundamental clue pointing to two entirely different kinds of cosmic engine. The theoretical link is as dramatic as the bursts themselves. Long gamma-ray bursts, those drawn-out events, are now understood as the death cries of the universe's most massive stars. In a cataclysm called a collapsar, a star many times heavier than our Sun exhausts its nuclear fuel. Its core collapses directly into a black hole, while the outer layers crash inward and then erupt outward in hyper-energetic jets that drill through the star. The burst we see is the jet breaking through the stellar surface, a final, brilliant beacon signaling the birth of a black hole from a star's ruin. Short bursts, however, tell a different, even more violent tale. They are thought to be the product of a merger, the final, fatal dance of two ultra-dense stellar corpses, either neutron stars or a neutron star and a black hole. After spiraling together for eons, they collide in a titanic impact that sends ripples through spacetime itself, and for a brief, glorious instant, fuses material into a blaze of gamma rays. One is a stellar death, the other a stellar collision. This is where the GBM's specific capabilities become absolutely critical. its fast spectroscopy, its ability to immediately break down the energy of the incoming photons provides a quick fingerprint of the event. And its rapid localization is the essential first step. For a long burst, the fading afterglow is often bright enough that other telescopes have a longer window to find it. But a short burst is a cosmic blink and you miss it event. Its afterglow fades extraordinarily quickly. If you do not know exactly where to look within moments, the chance is lost forever. The GBM's ability to calculate a sky position within seconds and sound the alarm is what makes studying short bursts possible at all. This capability led to one of the most monumental discoveries in modern astronomy. On August 17, 2017, the GBM detected a short, sharp burst of gamma rays. Almost simultaneously, a new kind of observatory, the Laser Interferometer Gravitational Wave Observatory, felt a tremor in the fabric of spacetime, a ripple from a cosmic collision. The timing was perfect, and the location from the GBM matched the rough sky area from the gravitational wave signal. This event, known as GW170817, was the historic first detection of both light and gravitational waves from the same source, confirming beyond doubt that the merger of two neutron stars creates a short gamma-ray burst. The GBM's alert was the crucial link that told optical telescopes where to point, leading to the identification of the host galaxy and the observation of a kilonova, the radioactive glow of heavy elements like gold and platinum forged in the merger. In that moment, the monitor did more than classify a burst. It connected the invisible warp of spacetime to the visible light of creation, revealing the violent origin of the very elements that make up our world. But this cosmic partnership goes far beyond a simple division of labor. The GBM's 14 watchful eyes and the large area telescope's single, piercing gaze were designed from the beginning to work in concert, creating a scientific instrument far greater than the sum of its parts. Their differences are their greatest strength. The gamma-ray burst monitor is the ultimate generalist. Its detectors are sensitive to lower energy gamma rays, typically in the range of 8,000 to 40 million electron volts. More importantly, its placement gives it an enormous, unshielded field of view. At any moment, it can see about 70% of the entire sky, making it almost impossible for a bright transient event to escape its notice. It is the perfect sentinel, the instrument that never blinks. The Large Area Telescope, however, is the specialist. It sees a much narrower slice of the sky at any one time, about 20%, but it peers into a far more extreme realm of energy. It detects gamma rays from 20 million to over 300 billion electron volts, venturing into a territory where particles carry the punch of those produced in our most powerful particle accelerators on Earth. This high-energy vision allows it to see the most violent processes within an explosion, the mechanisms that accelerate particles to near light speed. When a gamma-ray burst erupts, this partnership springs to life in a beautifully orchestrated sequence. Often, it is the GBM that sounds the alarm. Its rapid trigger and rough localization provide the first crucial data point, the when and the approximate where. This alert is not just for ground-based telescopes, it is also for its partner Onboard. The Fermi spacecraft can autonomously use the GBM's initial coordinates to execute a quick maneuver, a slewing motion that repoints the entire observatory to bring the burst location into the much narrower field of view of the Large Area Telescope. Now the high-energy investigation begins. While the GBM captures the broad, sweeping profile of the burst at lower energies, the LET searches for the event's most energetic photons. If it finds them, it can localize the source with pinpoint accuracy, often to within a few arcminutes, which is like pinpointing a single house in a vast metropolitan area from orbit. This precise location is then immediately relayed to astronomers, refining the search for an optical or radio afterglow. But the real magic is in the combined data. By stitching together the GBM's low-energy spectrum and the LET's high-energy spectrum, scientists get a complete energy budget of the explosion. It is like having both a thermometer and a barometer in a storm. The GBM measures the heat and duration, while the LET measures the intense pressure and the most powerful gusts. Together, they reveal the total power output, the behavior of the relativistic jets, and the physics of the shock waves that generate the light across this incredible energy range. This synergy transforms a flash in the dark into a multidimensional portrait, allowing us to dissect the engine of a cosmic catastrophe from its first spark to its final, fading echo across the highest energies the universe can produce. The data from these cosmic cataclysms arrives not just as sterile numbers, but as stories written in light, stories that sometimes only the human eye can truly decipher. This is where the search moves from orbit to the living room, through an extraordinary project called Burst Chaser. Hosted on the Zooniverse platform, this NASA citizen science initiative opens the vault of the Gamma-Ray Burst Monitor's archives to anyone with curiosity and an internet connection. Volunteers are presented with the actual light curves, the graphs of brightness over time from thousands of detected events. Their task is deceptively simple, yet profoundly important, to look at the shape of each burst and help classify its structure. Does the light curve show a single, smooth peak or a complex series of frantic spikes like a heartbeat in distress? Is there a faint precursor flash before the main event or a quiet bump in the tail long after? While computers are excellent at measuring the raw numbers, the human brain remains unparalleled at pattern recognition, at spotting the odd and the unusual that might slip past an automated algorithm's rigid criteria. By having thousands of volunteers examine the same data, scientists achieve a powerful consensus, filtering out random noise and homing in on the truly unique signatures. This human-in-the-loop approach is vital for mining the vast GBM dataset. Over its years in orbit, the instrument has recorded hundreds of thousands of triggers, far more than any small team of researchers could ever scrutinize in detail. Within that mountain of data could lie subtle anomalies, rare hybrids of burst types, or entirely new classes of high-energy transients that we do not yet have a category for. A volunteer might be the first to notice a peculiar double-peaked structure in a short burst, or a strangely slow rise in a long one, clues that point to new physics in the explosion engine. Every classification click contributes to a living map of cosmic violence, helping astronomers prioritize which events deserve deep follow-up study. In this way, Burst Chaser transforms the passive act of observation into a collective act of discovery. It democratizes the frontier of astrophysics, allowing anyone to become a direct participant in the journey, to look at the same raw data as a NASA, a scientist, and help write the next paragraph in our understanding of the universe's most extreme events. Creating an instrument to see the invisible requires a delicate balance of brute strength and exquisite sensitivity. The detectors of the Gamma-Ray Burst Monitor are not delicate laboratory crystals, they are ruggedized marvels engineered for a violent ride. Each sodium iodide and bismuth germanate crystal is mounted within a rugged housing, designed to withstand the bone-shaking vibrations and crushing G-forces of a rocket launch. They must then operate flawlessly in the vacuum of space, enduring wild temperature swings from the blistering direct sun to the deep freeze of Earth's shadow, all while being bombarded by a continuous rain of cosmic rays that could degrade or confuse lesser instruments. The engineering challenge was profound. Build a system sensitive enough to detect a single photon from a galaxy billions of light years away, but tough enough to survive the trip to orbit and function for years without any hope of physical repair. Every component, from the photomultiplier tubes to the power supplies, was subjected to punishing tests, shaken, baked, frozen, and irradiated in vacuum chambers to simulate a decade of abuse in just months. This rigorous qualification process ensured the hardware would not just survive but perform with unwavering precision. Yet, building a robust detector is only half the battle. The true foundation of trustworthy science is calibration. Before launch, each detector was meticulously characterized on the ground. Scientists exposed them to known radioactive sources like cesium-137 or cobalt-60, which emit gamma rays at very specific, predictable energies. By seeing how the instrument responded to these known signals, they created a detailed map, a translation guide between the tiny flash of light in the crystal and the actual energy of the incoming photon. But the calibration does not end at launch. The environment in space is different and components can age, so the GBM performs continuous self-calibration in orbit. It uses the predictable background of cosmic rays, a steady drizzle of high-energy particles from across the galaxy, as a constant reference point. It also monitors known, steady astrophysical sources like the Vela pulsar, a celestial lighthouse that emits regular pulses of gamma rays. By checking that these familiar cosmic beacons still register at their expected energies and rates, the team can verify the instrument's health and adjust its sensitivity over time. This relentless dedication to calibration is what transforms raw electrical signals into scientific truth. It ensures that when the GBM reports a photon at 94 billion electron volts from a distant burst, we can trust that measurement with absolute confidence. That trust is the bedrock upon which every discovery, from stellar collisions to atmospheric lightning, is built, turning flashes in the dark into data that reshapes our universe. Behind every automated alert is a team of watchful guardians on the ground. At NASA Goddard Space Flight Center and the Marshall Space Flight Center, a dedicated crew of scientists and engineers begins each shift with a quiet ritual of checks and balances. Their first task is a thorough health assessment of the gamma-ray burst monitor itself, a process akin to a doctor taking a patient's vital signs from millions of miles away. They examine telemetry data streaming down from Fermi, reviewing power levels, detector temperatures, and background radiation rates. Any subtle drift or anomaly could affect the quality of the science, so this daily diagnostic is the foundation of all trust in the data. It is a quiet, meticulous process, ensuring the sentinel in the sky remains in perfect health. Next, they review the log of automated triggers from the previous 24 hours. The instrument's algorithms are excellent, but they are not infallible. The team sifts through dozens of entries, most of which are false alarms, glitches from charged particle hits, or flashes from our own sun. Their trained eyes look for the telltale signatures of a real astrophysical event, comparing the trigger data across all 14 detectors and checking it against other space-based monitors. This validation step is crucial. It prevents the astronomical community from chasing ghosts and ensures that every public alert carries the weight of human confirmation. Beyond routine monitoring, the team also plans for special observations. They might adjust the instrument's sensitivity for a coordinated campaign to study a known magnetar or prepare for a predicted solar flare. Their work is a blend of long-term strategy and instantaneous reaction. Then it happens. A distinctive tone chimes on a workstation, and a bright banner flashes across a monitor burst trigger. The quiet focus of the operations room snaps into a different kind of intensity. This is the moment their entire routine prepares for. Within seconds, they are analyzing the initial data packet, confirming the burst's reality, refining its position, and authorizing the rapid alert to be sent to the global network. There is a palpable, shared excitement, a quick exchange of glances and a race against the clock, not with panic, but with the precision of a well-rehearsed emergency response. One engineer described the feeling as a sudden connection to the cosmos, a reminder that their screens are not just displaying numbers, but the raw aftermath of a stellar death or collision that occurred billions of years ago. They are the first humans to know it happened, translating the machine's binary scream into a call to action for telescopes across the planet. This human element transforms the GBM from a robotic instrument into an extension of our collective curiosity, a partnership between silicon vigilance on orbit and human intuition on Earth, forever watching for the next flash in the eternal dark. Beyond the cataclysmic deaths of stars lies a deeper, colder mystery. The universe is filled with something we cannot see, a ghostly substance that binds galaxies together and dictates the cosmos's very structure. We call it dark matter. It does not emit, absorb, or reflect light, making it utterly invisible to every traditional telescope ever built. Yet its gravitational pull is undeniable, sculpting the cosmos on the largest scales. So how do you search for something defined by its refusal to be seen? You look for the shadows it might cast in the most energetic light. This is where the gamma-ray burst monitor, an instrument built to watch for explosions, finds itself on the frontier of one of physics' greatest quests. The leading theoretical candidates for dark matter are particles known as weakly interacting massive particles. True to their name, they would interact with ordinary matter only through gravity and the weak nuclear force, passing through our planet and our bodies as if we were not even there. But according to some compelling models, these particles are not entirely inert. In regions of incredibly dense dark matter, like the cores of dwarf galaxies or the heart of our own Milky Way, two of these WIMP could occasionally collide. When they do, the theory suggests they might annihilate each other in a silent flash, converting their mass directly into energy and producing a spray of standard particles, including gamma rays. Alternatively, a single, unstable dark matter particle could spontaneously decay, releasing a burst of gamma-ray energy with a very specific signature. This is the tantalizing possibility. Dark matter might reveal itself not by what it is, but by the light it could indirectly create. The GBM enters this search not as a specialist, but as a vigilant witness to the entire gamma-ray sky. While it scans for bursts, it is also constantly measuring the diffuse gamma-ray background, the faint, omnipresent glow of high-energy light that fills the universe. Scientists meticulously analyze this background data, searching for subtle anomalies. They look for an unexplained excess of gamma rays streaming from the direction of dwarf spheroidal galaxies, which are thought to be almost pure dark matter, with very few stars to create conventional gamma ray signals. They scrutinize the data from the galactic center, where dark matter should be densest, hunting for a faint spike at one very precise energy, a spectral line that would be the smoking gun of particle annihilation or decay. The GBM's strength here is its all-sky monitoring and its large collection area, gathering a vast amount of data over years. While it may not have the ultra-fine energy resolution of some dedicated dark matter telescopes, its longevity and wide gaze make it a powerful tool for surveying the sky for any broad, unexpected excesses that other instruments might miss. Every flash it catches from a dying star is recorded against this quieter, more mysterious backdrop. So with every gamma-ray burst it announces, the GBM is also silently gathering data on the empty spaces between them, on the faint, uniform glow that might, one day, contain the whisper of the universe's most elusive substance. It is a reminder that our tools can often see more than we initially designed them for, turning a watchman for stellar catastrophes into a silent hunter of cosmic ghosts. The universe's most violent explosions arrive not as sound, but as silent spikes of light on a graph. Yet hidden within those jagged lines is a rhythm, a cadence of creation and destruction waiting to be heard. This is the art and science of data sonification, where the gamma-ray burst monitor's precise measurements are translated into sound, giving a voice to the cosmos. The process begins with a light curve, the graph of a burst's brightness over time. Time itself becomes the timeline of an audio track. The vertical axis, the intensity of the gamma rays, controls the volume. A sudden, sharp spike in brightness becomes a loud, percussive crack. A long, rolling burst with multiple peaks transforms into a series of building and fading tones like distant thunder. But it goes deeper. Scientists can map other data dimensions into the sound. The energy of the photons, for instance, can be mapped to pitch. As a burst evolves and the average energy of its gamma rays shifts, you might hear the tone slide from a low rumble to a high, thin whine. This spectral evolution tells a story of changing physics within the explosion, and now you can hear it unfold. A short, hard burst from colliding neutron stars might sound like two sharp, snapping claps. A long, complex burst from a dying star could resemble a chaotic symphony with overlapping notes and a slow, rumbling decay. For some researchers, especially those with visual impairments, sonification offers a powerful analytical tool. The human ear can detect subtle patterns in timing and rhythm that the eye might miss on a graph, revealing hidden structures within the data. But for everyone, it serves a profound purpose in outreach. It makes the abstract tangible. You are not just looking at a line on a screen, you are listening to the heartbeat of a cataclysm billions of light years away. It connects us to these events on a visceral, almost emotional level. The silent flash of a dying star becomes a shout in the dark, a merger becomes a cosmic drumbeat. This auditory bridge transforms raw data into an experience, reminding us that science is not just about numbers, but about perceiving the universe in every way we can. The same detectors that catch dying stars also catch our own planet's lightning turned inside out. While scanning the cosmos, the gamma-ray burst monitor has recorded hundreds of sudden, intense flashes coming not from deep space but from the storm clouds swirling below. These are terrestrial gamma-ray flashes, and they are among the most energetic natural phenomena on Earth. A single TGF packs a staggering punch, releasing a burst of gamma-ray radiation in less than a millisecond, a blink so fast it makes a camera flash seem slow. This energy is born not from nuclear processes, but from the raw, chaotic power of a thunderstorm. The leading explanation for this incredible phenomenon is a process called relativistic runaway electron avalanche. Picture the intense electric fields inside a towering thundercloud, especially near its top. These fields can become so powerfully strong that they act like a natural particle accelerator. A single free electron, perhaps knocked loose by a cosmic ray, gets caught in this field. It is accelerated to nearly the speed of light. As it screams through the atmosphere, it smashes into the nucleus of an air molecule, shattering it and releasing more high-speed electrons. Those new electrons are also accelerated, and they, in turn, smash into more molecules. In a chain reaction that unfolds in microseconds, this creates an avalanche of relativistic electrons, all moving at a significant fraction of light speed. The final step is the gamma-ray flash itself. When these ultra-fast electrons are suddenly decelerated by colliding with other atoms, they shed their enormous kinetic energy by emitting gamma-ray photons. It is a process known as bremsstrahlung, or breaking radiation. In essence, the thundercloud's electric field acts as a natural slingshot, flinging particles to incredible speeds, and the sudden stop against the atmosphere creates the brilliant, invisible flash that the GBM sees from above. This discovery has fundamentally changed our understanding of thunderstorms. We once saw them as purely meteorological events producing rain, lightning, and thunder. Now, we know they are also powerful natural particle accelerators, capable of generating the same kind of radiation found in medical X-ray machines or particle colliders, but on a planetary scale. By cataloging hundreds of these events from orbit, the GBM provides a unique census. It reveals where and when these flashes occur most frequently, their energy distribution, and their relationship to lightning strokes. This data is helping atmospheric physicists model the extreme electric fields inside storms, fields that are too dangerous and transient to measure directly from within the clouds. The monitor's downward glance has turned a familiar weather event into a frontier of high-energy physics, proving that some of the universe's most violent processes are not just out among the stars, but raging right in the sky above our heads. That invisible lightning from Earth storms is a whisper compared to the cosmic quakes of a magnetar, Among the neutron stars, the dense corpses of massive suns, magnetars are the true monsters, possessing magnetic fields of almost incomprehensible strength. To grasp the scale, the most powerful magnet you might hold has a field of about 1 Tesla. A hospital MRI machine operates at around 3 Tesla. A neutron star's typical field is 1 trillion Tesla. But a magnetar, its magnetic field is 1,000 times stronger still, 1 quadrillion Tesla. This is a force so potent it literally warps the structure of reality around the star, creating a zone where atoms are stretched into long, thin needles and quantum effects dominate. These fields are not static, they are dynamic and incredibly stressed, constantly twisting and straining the star's solid, crystalline crust. This stress builds until it must be released. The crust cracks, a starquake occurs. It is not an earthquake of shifting tectonic plates, but a fracture in a crust of iron nuclei packed into a lattice as dense as an atomic nucleus, under the grip of that impossible magnetic field. When it slips, the entire star rings like a bell, and the pent-up magnetic energy is unleashed in a flash of gamma rays. We see this as a soft gamma repeater, a sudden, bright burst of slightly lower energy gamma rays that can happen again and again from the same object. The gamma-ray burst monitor is perfectly tuned to catch these events, cataloging their timing, energy, and rhythm to map the interior and magnetic life of these extreme stellar corpses. But sometimes a starquake is not a crack, it is a cataclysm. On December 27, 2004, a magnetar named SGR 180620, located about 50,000 light-years away in our own galaxy, experienced an event so violent it defied belief. It produced a giant flare. For 1/5 of a second, this single object outshone the full moon, becoming the brightest gamma-ray source ever seen outside our solar system. The total energy released in that initial spike was more than our sun will emit in 250,000 years. The flash was so intense that it actually affected our planet. It ionized atoms in Earth's upper atmosphere, disrupting long-range radio communications for several minutes. Instruments not designed for such an event, like satellites and even ground-based radiation monitors, were briefly overwhelmed. If this flare had occurred within 10 light-years of Earth, it could have severely damaged our ozone layer with drastic consequences for life. This was a stellar tantrum of existential proportions. This is why the GBM's constant watch is so vital. By monitoring the more frequent, smaller outbursts from magnetars, scientists can study the buildup of stress in these magnetic monsters. They can test models of how the crust fails and how the magnetic field reconnects, a process where magnetic field lines snap and rejoin, releasing torrents of energy. On a magnetar, this is not a solar flare, it is magnetic reconnection on a scale where the field strength distorts the vacuum of space itself. The GBM provides the data to understand the physics of matter and magnetism under conditions no laboratory will ever replicate. Each soft burst is a probe into the heart of a star where the rules are written by forces 1 quadrillion times stronger than anything on Earth, teaching us about the final, furious chapters in the life of matter. 16 years in the punishing environment of space is a testament to brilliant engineering and a little bit of luck. Designed for a primary mission of 5 years, the Fermi Gamma-Ray Space Telescope and its Gamma-Ray Burst Monitor have not only survived but thrived, operating with remarkable health and vigor. This extended lifespan is a gift to science, a bonus round of observation that has transformed our understanding from a series of snapshots into a rich, moving picture of the high-energy universe. Every extra day in orbit is another chance to catch a rare event, to monitor a source as it evolves, and to build the statistical foundation needed to solve deeper mysteries. The mission's goals have elegantly evolved with its longevity. First, it continues to build the statistics for rare events. Think of phenomena like the neutron star merger that produced both gravitational waves and gamma rays. That was a once-in-a-generation detection. To truly understand the population of these events, how often they occur and in what varieties, we need to catch more of them. The GBM's relentless watch increases the odds with every passing year, slowly filling in the blanks in our cosmic census of catastrophe. Second, it monitors the changing sky. The gamma-ray universe is not static. New magnetars awaken with violent starquakes, active galaxies flare unpredictably, and even our own sun goes through cycles of stormy activity. The GBM's constant, all-sky data provides a long-term baseline, a decade-plus light curve for the entire high-energy sky. This allows astronomers to study not just what these objects do in a single outburst, but how they behave over years, revealing patterns and life cycles we could never see in a shorter mission. Finally, and perhaps most crucially, it serves as the essential trigger for a new generation of observatories. As gravitational wave detectors like LIGO and Virgo become more sensitive, and as new instruments like the Vera-C Rubin Observatory prepare to scan the entire visible sky every few nights, the GBM's rapid alerts are more valuable than ever. It provides the instantaneous, precise coordinates that tell these powerful new tools exactly where to look, orchestrating a symphony of multi-messenger astronomy where light, gravitational waves, and even neutrinos are observed together. The GBM has become the veteran sentinel, the experienced watchkeeper that guides the eyes of newer, more specialized instruments to the action. So what comes next? What might a future gamma-ray monitor, learning from the GBM's unparalleled success, look like? It would likely be even faster, with onboard processing capable of more sophisticated real-time analysis to filter signals with greater precision. Its detectors might cover an even broader energy range, seamlessly bridging the gap between the GBM's domain and the highest energies seen by its partner, the Large Area Telescope. We could envision a future where a network of smaller gamma-ray monitors are deployed across the solar system, on spacecraft orbiting other planets or even stationed at Lagrange points, creating a vast interferometer for gamma rays. This would allow for instantaneous, incredibly precise triangulation of bursts, pinpointing their location to a tiny fraction of the sky within seconds. Such a network would not only tell us where to look, but could also help us measure the expansion rate of the universe in an entirely new way. The legacy of the gamma-ray burst monitor is already written in thousands of alerts, in textbooks rewritten, and in the gold forged from neutron star collisions that we now know we wear on our fingers. Its greater legacy, however, will be the blueprint it provides, a proven design for vigilance that will undoubtedly shape the watchful eyes we turn to the cosmos for decades to come. The silent flash of a gamma-ray burst is no longer a solitary clue. We have entered an era where we can feel the universe's tremors and taste its ghostly particles, a revolution called multi-messenger astronomy. For centuries, astronomy meant studying light, from the gentle glow of starlight to the violent punch of gamma rays. But now we are learning to read the cosmos with a full sensory palette. We detect the ripples in spacetime itself, gravitational waves, from colliding black holes and neutron stars. We catch elusive neutrinos, nearly massless particles that travel unimpeded from the hearts of galaxies. We sample cosmic rays, atomic nuclei accelerated to fantastic speeds. Each messenger tells a different part of the story. Light shows us the aftermath, the heat and the glow. Gravitational waves reveal the choreography of massive bodies in motion. Neutrinos point directly back to the engine, the site of particle acceleration. But to solve the cosmic puzzle, you need to match the pieces from different messengers, and you need to do it fast. This is where the gamma-ray burst monitor's decades of experience become absolutely indispensable. It is the fastest, most reliable tripwire for the electromagnetic side of the equation. When the Laser Interferometer Gravitational Wave Observatory and Virgo feel a tremor from a neutron star merger, they can only provide a vast, fuzzy patch of sky, hundreds of times larger than the full moon, filled with millions of galaxies. Finding the needle in that haystack requires a flash of light to guide the search. The GBM's simultaneous detection of a short gamma-ray burst provides that crucial beacon, shrinking the search area dramatically and telling optical telescopes precisely where to point. This partnership made history in 2017, confirming that mergers forge heavy elements and connecting a gravitational wave signal to a visible kilonova for the first time. The same rapid alert capability is vital for neutrino astronomy. When the Ice Cube Neutrino Observatory, a cubic kilometer of ice buried at the South Pole, detects a single high-energy neutrino from deep space, it too sends out an alert with a rough direction. If that neutrino was created alongside a gamma-ray flare, perhaps from a blazar's jet or a tidal disruption event, the GBM's all-sky data is immediately scanned. Finding a coincident gamma-ray flash in the same part of the sky and at the same moment turns a solitary ghost particle into a located cosmic event, unveiling the specific galaxy and the mechanism that launched it. The GBM sits at the nerve center of this global network. Its alerts trigger a cascade of automated observations across every continent and in orbit, from radio dishes to X-ray telescopes. This coordinated effort, with the GBM as the rapid response coordinator for light, is what transforms a collection of disparate signals into a unified narrative. It is how we are rewriting textbooks in real time, moving from observing the universe in one language to understanding its full, multi-dimensional story. This data pipeline does not end in research papers. It flows directly into classrooms and computer labs around the world. The torrent of information from the gamma-ray burst monitor is not locked away. It is a public treasure, meticulously archived and made freely available to anyone with an internet connection. NASA Fermi Science Support Center provides user-friendly tools and software, allowing a high school student in Ohio or an undergraduate in Kenya to download the same light curves and spectra that professional astrophysicists use. They can measure the duration of a burst, analyze its energy spectrum, and even attempt their own classifications. This is not simulated data, it is the real signal from space, turning abstract concepts about cosmic explosions into hands-on, tangible inquiry. By lowering the technical barrier, the mission democratizes discovery, inviting a new generation to participate in the scientific process from their very first day. To bridge the gap between this raw data and a lesson plan, NASA created the Fermi Teacher Fellowship Program. Each year, a select group of educators embarks on an intensive summer collaboration with Fermi scientists at Goddard Space Flight Center. They are not just given a pre-packaged slide deck, they are immersed in the research. A physics teacher might work alongside a specialist to develop a new classroom activity that lets students sonify a gamma-ray burst, hearing the difference between a short merger and a long collapsar. A middle school science teacher could help create a simplified data visualization tool that plots burst locations on a map of the sky, revealing the isotropic nature of these explosions. These fellows return to their schools as ambassadors, equipped with authentic resources and the first-hand experience of how science actually works. Their students learn not just facts, but the process of asking questions, manipulating real data, and dealing with its inherent noise and uncertainty. The impact is profound and immediate. Across universities, undergraduate researchers are regularly publishing papers using GBM data. A team at Sonoma State University, for instance, used years of GBM observations to conduct a large-scale search for faint, repeating signals from magnetars, contributing to our statistical understanding of these objects. Another project at the University of Alabama in Huntsville had students analyzing the very first milliseconds of short bursts, looking for subtle precursors that might reveal the dynamics of the neutron star collision itself. These are not make-work projects, they are genuine contributions to the field, often presented at major conferences and published in journals. For a young scientist, there is no greater inspiration than knowing your analysis of real satellite data might reveal something new about the universe. It transforms astrophysics from a distant subject in a textbook into an active, accessible pursuit. The GBM's legacy, therefore, is measured not only in the black holes it has witnessed born or the elements it has seen forged, but in the thousands of young minds it has ignited. By handing them the keys to the universe's most violent events, it ensures the watch for flashes in the dark will continue for generations to come. The jagged line of a gamma-ray burst light curve is more than a graph, it is a signature of creation. This raw scientific data, a sequence of numbers representing the universe's most violent energy, has begun to escape the confines of research papers and find a second life in the world of art. Across studios and digital canvases, artists are collaborating with scientists, using the actual outputs from the gamma-ray burst monitor as their muse and their medium. They are not illustrating science, they are interpreting it, translating the invisible and the abstract into forms that speak to our emotions and senses. One visual artist might take the precise light curve of a historic burst, like GRB 130427A, and use its peaks and valleys to dictate the brushstrokes of a vast, swirling painting, where the intensity of the gamma rays determines the thickness of the paint or the brightness of a color. The chaotic spike of a short burst becomes a sharp, angular sculpture in metal, while the rolling structure of a long burst inspires a flowing, layered textile piece. The data provides the structure, the rigid truth of the event, and the artist imbues it with texture, color, and human feeling. In the realm of music, composers go beyond simple sonification. They use the spectral data, the breakdown of energy over time, to create intricate musical scores. The shift from low energy to high energy photons might guide a transition from deep cello notes to the piercing cry of a violin, with the duration of the burst setting the tempo of the entire piece. A digital installation artist might project real-time GBM data onto a massive wall, allowing the audience to stand within a visualization of the cosmic background, watching as new bursts from across the universe flash into existence around them, each one triggering a unique sound and light pattern. This fusion does something remarkable. It creates a new pathway for public engagement. Someone who might never read an astrophysics journal can be drawn in by the haunting beauty of a data-driven sculpture. They feel the power of the event before they understand the physics behind it. That emotional resonance becomes a bridge. It prompts questions. What created this beautiful, terrifying pattern? Why does this data from space feel so dramatic? The art becomes a doorway, inviting the viewer to step through and learn about magnetar's stellar collapse and the mission that captured the signal. This collaboration also enriches the scientist's own perspective. Seeing their data reimagined through an artist's lens can reveal patterns or emotional contours they had not consciously considered. It reaffirms that this work is not just about collecting numbers, but about bearing witness to profound cosmic stories. The art born from gamma-ray bursts stands as a testament to a shared human impulse. Whether through equations or through canvas, we are driven to capture, interpret, and find meaning in the flashes that illuminate our mysterious universe. Even the most vigilant sentinel sometimes sees ghosts in the machine. The pristine data stream from the gamma-ray burst monitor is not immune to the chaotic environment of space, and some of the most intriguing detective work involves figuring out what is real and what is merely an electronic phantom. One persistent source of these ghosts is a region of space known as the South Atlantic Anomaly. Here, Earth's protective magnetic field dips unusually close to the planet's surface, allowing the inner Van Allen radiation belt, a zone of trapped high-energy particles, to come much closer to our atmosphere. Every time the Fermi spacecraft, moving at 17,000 miles per hour, passes through this region, it flies through a soup of intense radiation. For the GBM's sensitive detectors, it is like sailing into a sudden, violent hailstorm. The crystals are bombarded by protons and electrons, creating a cacophony of false signals that can mimic the sharp rise of a genuine astrophysical burst. The instrument's onboard software is trained to recognize the distinctive signature of this passage, but sometimes a particularly intense particle shower can trip the trigger, generating a false alert that must be caught and dismissed by the watchful team on the ground. Then there are the cosmic rays themselves, atomic nuclei from distant supernova traveling at nearly the speed of light. When one of these particles slams directly into a detector, it can deposit a huge amount of energy all at once, creating a signal that looks for a single data point, like an incredibly energetic photon from a cosmic explosion. But a real gamma-ray burst is not a single spike, it is a shower. Scientists must distinguish between the solitary bang of a cosmic ray strike and the statistical chorus of many photons arriving from one direction in space. This requires sophisticated filtering, comparing the rates across multiple detectors, and analyzing the shape of the energy deposit within the crystal itself. Diagnosing these issues is a continuous exercise in forensic science. The operations team maintains a detailed log of known instrumental behavior. They have maps of the South Atlantic anomalies effects, models of cosmic ray interaction rates, and catalogs of every previous glitch. When a new anomaly appears, they compare it against this library of known ghosts. They ask specific questions. Did the event occur during a scheduled passage through the anomaly? Do the signals from all 14 detectors show a pattern consistent with a single astrophysical direction, or is it chaotic as expected from a local particle shower? Sometimes they can even correlate the event with data from other spacecraft monitoring space weather, checking if a solar flare or a surge in the solar wind could have been the culprit. This meticulous process of elimination is what maintains the integrity of the entire scientific endeavor. Every public alert, every published paper, rests on the foundation that these signals have been vetted, that the ghosts have been identified and separated from the true whispers of the cosmos. It is a humble reminder that to see the universe clearly, we must first understand the imperfections in our own eyes. Every guardian of the high-energy sky has its own way of watching. To truly appreciate the gamma-ray burst monitor's role, we must see it alongside its companions past and present in the orbital fleet. One of its closest partners is the Burst Alert Telescope, or BAT, aboard the Swift satellite. While both are masters of the rapid alert, their methods differ. Swift's BAT is a narrower, more focused hunter. It uses a coded mask, a patterned grid that casts a shadow onto its detector array, allowing it to pinpoint a burst's location with exquisite precision, often within a minute of arc. This is crucial for Swift's primary mission, to instantly slew its X-ray and optical telescopes to catch the fading afterglow. However, this precision comes with a trade-off, a smaller field of view. The BAT sees about 1/6 of the sky at any moment. The GBM, with its unshielded detectors, sees nearly 3/4 of it. Their spectral eyes are also tuned differently. The BAT sees slightly higher energy X-rays and soft gamma rays, while the GBM is sensitive to a broader, lower range. They are not competitors, they are a perfect team. Often, the GBM's wide net catches the first flash and provides the initial course coordinates. Swift, receiving that alert, can then point its BAT for a precise fix, turning the entire observatory to capture the multi-wavelength aftermath. This partnership exemplifies the GBM's core strength. It is the wide-angle lens that ensures nothing slips through the cracks. Its lineage traces back to a legendary predecessor, the Burst and Transient Source Experiment, or BATSE, on the Compton Gamma Ray Observatory in the 1990s. BATSE, with its 8 detectors mounted on the corners of the spacecraft, proved the all-sky monitoring concept. It was BATSE's data that definitively showed gamma-ray bursts were distributed evenly across the sky, proving they were cosmological, coming from far beyond our galaxy. The GBM is the direct descendant of that design, but with modern, more sensitive crystals and vastly improved electronics and software. It is BATSE's legacy, refined and extended for a new century of discovery. Looking ahead, future concepts for gamma-ray monitors imagine networks of nanosatellites or instruments with even faster response times and broader energy coverage. Yet, the GBM's specific niche remains uniquely vital. It is the workhorse of continuous, unbiased, all-sky surveillance in its specific energy band. While other missions may see deeper or localize better, no other current instrument provides the same relentless, wide-field vigilance. This makes it the indispensable heartbeat of the global time domain network. When a gravitational wave detector feels a ripple or a neutrino observatory catches a ghost particle, the first question astronomers ask is, did Fermi's GBM see a flash? Its constant watch provides the foundational context for the entire high-energy sky, a living map against which every other sudden cosmic event is measured. The invisible light from a dying star does more than rewrite textbooks, it quietly reshapes the world in your doctor's office. The relentless pursuit to build better gamma-ray detectors, like those in the gamma-ray burst monitor, drives innovation in materials and electronics that inevitably spin off into terrestrial technology. The quest to capture a single photon from billions of light-years away pushes scientists to develop ever more sensitive scintillator crystals and photomultiplier tubes. These advancements directly feed into the next generation of medical imaging devices. Positron emission tomography, or PET, scanners, which help diagnose cancers and map brain function, rely on the same fundamental physics, detecting gamma rays produced inside the body. Improvements born from space-based detector research can lead to clearer images with lower radiation doses for patients, turning the hunt for cosmic explosions into a tool for saving lives here on Earth. Similarly, the sophisticated radiation monitoring and spectroscopy techniques perfected for sifting cosmic signals from background noise enhance our ability to monitor for nuclear materials, ensuring safer ports and power plants. The technology built to understand the universe's fury becomes woven into the fabric of our security and health. On a deeper level, these discoveries perform a quiet recalibration of our perspective. Every gamma-ray burst the GBM records is a timestamp of a stellar death, a reminder that cataclysm is woven into the fabric of cosmic evolution. Our own planet's history is punctuated by similar violence, from asteroid impacts that altered the course of life to the searing radiation of nearby supernova that may have shaped our atmosphere. Understanding that the universe routinely produces explosions capable of sterilizing entire planets from across the galaxy forces a profound, almost philosophical shift. It underscores not just our fragility, but our incredible luck. We exist on a pale blue dot during a relatively quiet window in cosmic history, in a stable corner of a nondescript galaxy. The violence that forged the elements in our bodies, the gold in our jewelry, and the uranium in our soil is the same violence that could, from a slightly different distance or angle, erase us. This knowledge does not breed fear, but a profound sense of rarity and responsibility. It fuels the very human drive to look up and ask why. The GBM is not merely a machine, it is an extension of our innate curiosity, a manifestation of our refusal to be passive inhabitants of a mysterious cosmos. By building instruments to witness these events, we are asserting a need to comprehend our context, to map the forces that shaped our past and could dictate our future. Each flash localized, each burst classified, is a step out of the cave, a move from superstition to understanding. It connects the carbon in our cells to the heart of collapsing stars and the silicon in our detectors to the dust of ancient supernova. This work answers a fundamental human question: where do we come from? And in doing so, it transforms us from bystanders into active participants in a grand, ongoing story of cosmic evolution. The monitor's true gift is this connection, linking the technology in our hospitals to the explosions in the void, and our fleeting moment on Earth to the billion-year rhythms of the stars. These discoveries are not an end, but a gateway to deeper, more fundamental mysteries. We have mapped the landscape of cosmic explosions, but the precise engines that power them remain shrouded in theoretical speculation. What is the exact physical mechanism that launches a gamma-ray burst jet with such focused, relativistic fury? We know it involves a newborn black hole or magnetar and a swirling disk of superheated debris, but the transition from this chaotic maelstrom to a pencil-thin beam of matter moving at 99.9% the speed of light is a puzzle of plasma physics and gravity operating at their absolute limits. The gamma-ray burst monitor contributes crucial clues through timing. The fine structure within a burst's light curve, those millisecond spikes and dips, is a direct echo of the central engine's activity. By analyzing thousands of these curves, scientists can test models of jet formation, looking for signatures of magnetic field instabilities or shocks within the outflow itself. Each new burst captured adds another data point to constrain the theories, slowly narrowing down how the universe's most powerful particle accelerators are built. Beyond refining known categories, the GBM's long watch is essential for finding the outliers, the events that defy our current classifications. Are there entirely new classes of bursts waiting to be discovered? The search is on for ultra-long gamma-ray bursts, events that shine for tens of thousands of seconds, potentially from the collapse of supergiant stars or novel tidal disruption events. Conversely, could there be a population of incredibly faint, nearby bursts we have missed, events that would reveal a different, quieter pathway to stellar death? Finding these requires patience and a vast, consistent dataset. A single unusual event might be a fluke, but a pattern emerging from years of observations is a revolution. The GBM's uninterrupted, all-sky data provides the statistical bedrock for this search, allowing astronomers to sift through the archive for the subtle, the strange, and the singular. Even looking down at our own planet, profound questions remain. Terrestrial gamma-ray flashes have shown us that thunderstorms are natural particle accelerators, but what can they tell us about the very initiation of lightning itself? The relationship between a TGF and the subsequent lightning stroke is a key mystery. Does the avalanche of relativistic electrons actually trigger the main lightning discharge, or is it a spectacular side effect? By precisely timing TGFs detected from space and correlating them with ground-based radio networks that map lightning activity, scientists are using the GBM as a unique tool for atmospheric physics. Each detected flash is a probe into the heart of a storm's most intense electric fields, regions too dangerous for aircraft or balloons to penetrate. The long-term dataset allows researchers to see patterns, asking if certain types of storms or geographical regions are more prone to these energetic outbursts, gradually unraveling the connection between Earth's weather and the high-energy universe. Answering these questions, from the cosmic to the terrestrial, depends entirely on consistency. A flashy new instrument might see deeper, but it cannot see longer. The true power of the gamma-ray burst monitor lies in its decade-plus of continuous, calibrated observation. This longevity is what allows scientists to search for rare events that might only happen once a year, or to detect slow, subtle changes in the behavior of a magnetar over its lifetime. It provides the stable baseline against which every anomaly is measured. In cosmology, this consistent data might even help probe the expansion history of the universe. Some theorists suggest that the very high-energy gamma rays from distant bursts could interact with the diffuse fog of extragalactic background light, and by studying how the observed spectrum of bursts changes with distance, we might learn about the light from all the stars that has ever existed. This requires a large, uniform catalogue of bursts across vast distances, exactly what the GBM provides. Its role is evolving from a discoverer of explosions to a surveyor of the high-energy frontier. Its long-term gaze patiently collecting the clues that will, piece by piece, answer our biggest questions about how the universe works at its most extreme. That silent watchkeeper, the gamma-ray burst monitor, has now orbited our planet for over 16 years, a journey of constant vigilance that has rewritten our cosmic map. From its conception as a set of rugged crystals and photomultiplier tubes, engineered to survive the violence of launch and the harshness of space, to its role today as the rapid response heartbeat of the Fermi mission, its story is one of profound discovery. It began by listening for the universe's loudest screams. The gamma-ray bursts that signal stellar deaths and collisions, but its true genius was in hearing the whispers too. It catalogued the starquakes of magnetars, mapped the particle-accelerating fury of our own thunderstorms, and now serves as the essential electromagnetic partner in the new era of multi-messenger astronomy, linking gravitational waves and neutrinos to the light we see. Its legacy is measured in the heavy elements we now know are forged in neutron star mergers, in the textbooks updated with its data, and in the thousands of alerts that have guided telescopes across our planet to witness cosmic violence in real time. Yet for all it has revealed, the gamma-ray sky remains a frontier. The next great flash could be something entirely new, an anomaly that challenges every model we have built. The secrets of dark matter, the inner workings of the relativistic jet, the full spectrum of cosmic explosions, all of this still waits within the data stream flowing silently from orbit. This mission invites us all to stay curious, to follow the ongoing work of the Fermi team as they mine this rich archive. So the next time you look up at a clear night sky, remember the silent sentinel passing overhead, its unblinking detectors forever scanning the darkness. It is our proxy, our extended sense, watching for the next great flash that will, once again, illuminate the mysteries of our astonishing universe.